Welcome to the Explainer. Today, we're pulling back the curtain on the invisible engine that powers your computer, process management. It's the secret sauce that lets your machine juggle a million tasks at once without completely falling apart. So let's just start with something you experience every single day. Think about what your computer is doing right now. You might be writing an email, you've got music playing in the background, a notification just popped up. How on earth does it do all of that at the same time? It feels like magic, doesn't it? Well, it's not magic. It's just a very, very clever system. And the answer starts with understanding one really crucial difference, the difference between a program and a process. A program, well, that's kind of like a recipe just sitting on a shelf. It's a passive thing, just a set of instructions saved as a file. But a process, that's the chef in the kitchen, actively cooking that recipe. It's the program brought to life. And that's really the heart of it. A process is, simply put, a program in execution. The second you double-click an icon, the operating system grabs that program, loads it into memory, and poof, it becomes an active process. It is the fundamental unit of work that your OS has to deal with. Now, a process is way more than just the program's code. It's the whole package. Of course, it's got the code itself, but it also has its current activity. Think of the program counter as a little bookmark, telling it exactly which instruction it's on. It has a stack for temporary data, a data section for its global variables, and a heap for any memory it needs to grab while it's running. It's a complete, self-contained world. And every single one of these processes goes on a little journey, a life cycle. It starts as new as it's being created, then it moves into the ready state, which is basically like waiting in line at the grocery store, waiting for the CPU. When it gets its turn, it's running. If it has to wait for something, like for you to type something, it goes into the waiting state. And finally, when the job is done, it's terminated. So you have to wonder, how does the operating system keep track of hundreds of these things all at once? It uses something called a process control block, or PCB. The best way to think about it is like a detailed ID card or a manager's clipboard for every single process. It tracks everything, its state, its program counter, its memory usage, all of it. And here it is. This is the secret behind the multitasking magic. Your computer, especially one with a single CPU core, isn't truly doing everything at once. What it's actually doing is called a context switch. It's using the information in that PCB to pause one process and start another one. And it does this so incredibly fast, we're talking thousands of times a second, that it creates this powerful illusion that everything's happening simultaneously. This whole rapid-fire juggling act is managed by schedulers. You've got the long-term scheduler, who's kind of like a bouncer at a club, deciding which new processes get to come into the system. But the real star of the show is the short-term scheduler. This thing is the dispatcher, working on a millisecond timescale, constantly picking the next process to get a slice of CPU time. It has to be unbelievably fast to maintain that multitasking illusion. But processes don't always work alone. In fact, a lot of them are designed to cooperate with each other. Why? Well, for all sorts of reasons. They might need to share information. Think of a spell checker working with your document. They can speed up a huge calculation by breaking it into smaller pieces. And honestly, it just makes building complex applications much more modular and convenient. So if they need to talk to each other, how do they do it? Generally, there are two main ways. First, there's shared memory. Think of this like a common pantry in a kitchen. Any process can go in and grab or leave information. It's really fast, but you need strict rules so they don't get in each other's way. The other method is message passing. This is more like having a kitchen porter who carries notes between chefs. It's a bit slower, but it's much more orderly and often a lot safer. Okay, so why does any of this matter in the real world? Well, this quote from our source material absolutely nails it. We've all been there, right? You open one poorly coded website and suddenly your entire browser just freezes up, taking all your other tabs down with it. That's the huge risk of a single process design. And that's where the solution pioneered by Google Chrome is just so brilliant. It uses a multi-process architecture. The main browser has its own process, sure, but, and this is the key, each website tab runs in its own separate renderer process. This means if one tab crashes, it's totally isolated. It can't take down the whole application. It is a perfect example of using process management to build a more stable, more secure browser. So when you put it all together, you realize this invisible dance of creating, scheduling, and managing processes is the absolute bedrock of modern computing. It's what makes our devices feel responsive, stable, and powerful enough to handle our crazy digital lives. And that leaves us with a really interesting final thought. For years, multitasking was this incredible illusion. But today, with multi-core processors, our computers can achieve true parallelism, genuinely running multiple processes at the exact same time. So what new challenges and what new opportunities does that create for the operating systems of tomorrow? That right there is the next frontier.